Okay, so let's take a look at this sample problem. So it says a portion of two large parallel non-magnetic sheets with a fixed uniform charge on one side. The magnitude of the surface charge density are sigma plus, look at this value, and for the positively charged sheet, and sigma minus for the negative charge sheet. Find the electric field A to the left of the sheet and between the sheet and then to the right. Okay. Okay, so here we have a sigma plus and sigma minus, and actually for this sigma plus it will generate E plus point to the left side on the left side and then point to the right side on the right side, and for this negative plate, it will generate the E field pointing to the right side on the left side and then pointed to the left side on the right side. Okay, so first we would like to calculate E plus to be sigma plus over 2 epsilon naught, okay, because it will generate on both sides, so we have this 1/2 factor. So this is 6.8 times 10 to micro is 10 to negative 6 over 2 times 8.85 times 10 to negative 12. So this will be 3.84 times 10 to the 5th power Newton per Coulomb. And then similarly, we can calculate E minus, which will be sigma minus over 2 epsilon naught. Okay, so we just plug in a number 4.3 times 10 to negative 6 over 2 times 8.85 times 10 to negative 12. So this will be 2.43 times 10 to the 5th power Newton per Coulomb. Okay, so for EL, so we have E plus minus E minus, okay, they point in the opposite direction. So EL will be E plus minus E minus, which will be this one subtract by this one, which is 1.41 times 10 to the 5th power Newton per Coulomb. And it will point to the left side. It will point to the left side because E plus is larger, okay? And then for the between, okay, EB is this part. Okay, so we can see that this E plus and E minus point to the same direction. So in such a way, we have a E plus plus E minus. So it will be 6.27 times 10 to the 5th power Newton per Coulomb, and it will point to the right side. And then finally, for the E right, E out, it will be, okay, we can see that E plus on the right side, E minus on the left side. So we have a E plus minus E minus, which will be 1.41 times 10 to the 5th power Newton per Coulomb, and it will point to the right side. Okay, so these three are the answers. Okay, so this one is pretty simple. We just let you know how to apply the formula we just derived. Okay. Okay, so finally for this part, we would like to learn about applying the Gauss law for the spherical symmetry. So in chapter 21, we have learned actually two shell theorem. Okay, at that time I just I just said you try to believe it is true. We don't try to prove it in any way. But here, by making use of the Gauss law, we can actually prove these two shell theorems. So for shell theorem 22.1, it actually says a shell of uniform charge attract or repel a charged particle that is outside the shell, as if the shell charge were concentrated at the center of the shell. 就是说，如果你有一个球壳有球壳有电荷均匀分布的话，就是在这个这个是球壳。那你在外面看的东西的话，就是像所有的电荷都集中在中心一样。Okay, so for this case, we first try to apply the Gauss law to surface S2. S2 is the one larger than that because we would like to concern the E field outside. So we assume a Gaussian surface with an even larger radius. So for which R is larger than capital R. Capital R is the shell, the radius of the shell. So we would find that it turns out to be like this. It turns out to be like this. Actually, we need to use the Gauss law, something like epsilon naught integration of E dot dA equals Q enclosed. Okay, so this Q enclosed is nothing but Q, and then for this part, we will have epsilon naught and then times E times 4 pi R squared, something like that, equals Q, and then we just keep E on the left side and then move the remaining variable to the right side, so it turns out to be like this. So which means according to Gauss law, we can verify that this shell theorem 1 is true. And then for the second one, it says if a charged particle is isolated inside a shell of a uniform charge, there is no electrostatic force on the particle from the shell. So actually it means that inside this shell with uniform charge on the surface, the E field inside it will be zero. Will be zero. Okay, applying Gauss law to the surface S1 for which R is less than capital R. Okay, for this S1, it encloses nothing, so the net flux will be zero, and then it is symmetry, so it should be all the way zero for, over the whole Gaussian surface. So which means that E equals zero for the inside part. And this is the second part of the shell theorem. Okay, so by making use of the Gauss law for this spherical symmetry, we can simply verify that, or simply prove that the shell theorem, the two shell theorems are correct. Okay, so here we try to make it more slightly more complicated. Okay, so here, rather than having a shell, we have a sphere, but for this sphere we have uniform volume charge density, 有一个均匀的体积的密度所以这些电荷是分布在整个球体的所有的位置Okay, so here if we try to find the E field for the outside part, okay, which means that if R is greater than the capital R is the radius of this sphere, okay, that will be something like that. Okay, so Q will be the total charge here. Okay, so it actually looks like all the charge are concentrated at the center. You can understand it simply by the shell theorem. you can consider the whole shell, the whole sphere is a lot of different shell with different radius. Okay, so for one, okay, you can consider all the charge are at the center, and then for all of the sphere with different radius, okay, all the charge are concentrated at the same center. Okay, so it turns out that all the charge for this sphere are concentrated at the center for this case. But inside the sphere, it will be a little bit more complicated. Okay, so here we need to define this volume charge density rho. Okay, rho to be like Q is the total charge of the whole sphere, and then capital R is the radius of this sphere, and then 4/3 pi R cube is the volume of a sphere. 就是球体的体积，球体的体积是4/3 pi R 立方啊。这个应该是高中的什么几何有学过吧？So actually, the total charge divided by the total volume will be the density, because the density is uniform over the whole volume. Okay, so here we also try to define another Gaussian surface with a radius r which is smaller than this capital R. So inside this Gaussian surface, we have Q enclosed. We have Q enclosed because we need to apply the Gauss law for this Gaussian surface. Okay, so we need to consider the Q enclosed by this Gaussian surface. So in such a way, this the volume enclosed by this Gaussian surface will be 4/3 pi small r cube rather than capital R cube. This is the whole. This is the whole sphere. This is the partially. This part we only consider the Gaussian surface or the volume enclosed by the Gaussian surface. But actually the density is uniform, so this one and this one should be the same. So in such a way, we can express Q enclosed in terms of small r, capital R, and Q, and 4 pi. So we can look at this part and this part. So actually we can cancel this 4 and this 4, this 3 and this 3, this pi and this pi. So remaining part is this Q enclosed, and then we'll move this R cube to the left side, and then swap left and right all together. So it turns out to be R cube over capital R cube here, and then times Q. So yeah, so it will be something like that. And then here we try to apply the Gauss law for this Gaussian surface. So first of all, we try to write out the epsilon naught equals times the surface integral of E dot dA, and then equals Q enclosed. So for the Q enclosed is actually this one. Okay, putting it here. And then for the left side, epsilon naught E, and then times 4 pi R squared, just as what we did before. And then finally, we can do some cancellation. We can cancel this R squared partially with this R cube down to an R. And then we keep this E on the left side, and then we move this to the right side. So 4 pi epsilon naught go to here, and then R times Q times R here, and then capital R cube is in the denominator. Okay, so here is the expression of the E field generated by this sphere, and then the R is smaller than this capital R, which means the E field inside this sphere. And actually, a quick observation is that this E field is proportional to the distance from the center. Okay, any questions? 有没有问题？没有问题。Okay, So in such a way, for the outside part, we have the expression like this, which is the original case. And then for the inside part, in the previous page, we just derived that E will be proportional to the R. E will be proportional to R. So in such a way, if we try to plot these two together in a single graph, the x-axis is the R, the distance from the center to the point we concern, and then the y-axis is the E field. Okay, so here is the radius of the sphere. So if R, small r is smaller than capital R, then this E field is linearly increased proportional to the this part is proportional to the R. And for this part, it is proportional, inversely proportional to R squared. Inversely proportional to R squared. Okay, so the peak will be at this point. Okay, if you just plug in small r to be capital R, then these two will be the same. These two will be the same. Okay, turns out to be Q over 4 pi epsilon naught capital R squared at this point. Okay, so here we have some additional example. Of course, this one is really complicated. I mean, for the math. Okay, so if you can understand that, then yeah, probably you are good at math. But if you can't really understand that, just try to take a look at it. Okay, so here it says a volume charge density of a solid non-conducting sphere of radius capital R equals 5.6 centimeter radius with radial distance small r as given by this. Okay, so here, okay, so this volume charge density is not uniform anymore. Okay, so here is proportional to R, proportional to small r. Okay, it asks you what is the total charge? What is the total charge? Okay, so here we try to calculate the total charge first. Okay, so the total charge will be a triple integral for the sphere, and actually like rho times dv, rho times dv. Okay, actually it's a sphere. And then rho is the volume charge density. So let us try to cut this sphere into many small parts. Okay, every small part is a dv, and then every part will have the rho. We have the rho as the volume charge density. So rho times v will be. Okay, so rho will be the charge for every small part, and then we try to use the integration to add all of them together. Will be the total charge in this sphere. Okay, so as much as this is a sphere, we will use the spherical coordinate， 叫做球坐标 coordinate. Okay, so for the spherical coordinate, it will be something like integration. So first of all, this is the rho. Rho is this one. We try to assume this one. We try to make it like rho s. Okay, we don't need to write a 33.4 p every time. So we try to make it like a rho equals rho s times r over capital R. So here we have rho s times r over capital R. And then for the dv, for the spherical coordinate, it will be looking like r squared sine of theta dr d theta d phi. Okay, what is this r, theta and phi? Actually, in the spherical coordinate, as long as you have a point and you're concerned, okay, you connect this point to the original point. Okay, the distance will be r. The distance will be r. And then if you try to project it project it to the xy plane, project it to the xy plane. Yeah, so this is the xy plane and then this is the z. Okay, project it to the xy plane. So this angle will be phi. This angle will be phi. And then the angle between this line and the z-axis will be theta. Okay, so yeah, I don't try to explain too much why it would be like that, but yeah, if you need to use it in the calculus class, probably you need to remember it. Probably you need to remember. 就是如果你在微积分的时候要用这个东西的话，其实是需要记住它的。我不确定你们有没有在修类似的课，因为我不在澳大读本科的。但是球坐标的这个转换的话，就是说，它有一些奇怪的东西跑出来啊，它这里有一个 r 平方，有一个 sin of theta， 它是经过一些偏微分的转换，它得出这些东西的。那我就不尝试去推导这个东西，你可以尝试在这个 Wikipedia 搜看这个 spherical coordinate， 如果你对数学有兴趣的话。那怎么积分呢？这个 dr 的话就是从0积分到大 r， 就是这个球的半径，很好理解。然后 theta 的话就是因为这个线呢跟这个 z 轴的夹角，最小的话是0度，最大的话放到下面的话是180度，就是如果它正的 z 方向的话是0度那反的话是180度，所以它最多的话是0到180度之间，所以是0到派。而这个 phi 的话是这个 xy 上面的投影，所以可以转满一圈的话，它可以从0转到2派从0转到2派。你看着有3个积分，它是不是很复杂？其实它不是很复杂。它最终的话 ，so it will be looking like some independent function to do the integration. So it turns out to be like rho s is a constant, so you can be putting outside. Capital R is also a constant. So we can separate it like here we have R and R squared. So altogether we have R cubed. So we have R cubed dr from 0 to R. And then for the d theta, we have a sine of theta. So we have an integration of a sine of theta d theta from 0 to pi. And for the phi, we cannot see any phi there. So it is something like this, okay? From 0 to 2 pi. Yeah, if you don't like this expression, you can just consider it is 1 times this d phi, okay? But actually, we can simply write it like this, okay? If you like, you can write it as a 1 times d phi. It is okay. Okay, so all these 3 integration is easy to calculate. This one will be r to the 4th power over 4. This one, the antiderivative will be negative cosine, and then evaluate from 0 to pi. Okay, so cosine of 0 will be 1, cosine of pi will be negative 1, so this one will be 2. And then we integrate this 1 from 0 to 2 pi, so it turns out to be 2 pi. So it turns out to be rho s over r times r to the 4th power over 4 times 2 times 2 pi. Okay, so actually we can do some cancellation. This 2, and this 4, and then this r, and then this r to the 4th power down to r cube. So this answer will be pi rho s and then times r cube. Okay, and finally we can plug in all the numbers. 3.14 for the pi, and then times rho s is this one, 35.4 times 10 to negative 12, and then times r cube is this one, 0.056 cube. Okay, so when you press the calculator, you know that this one is 1.95 times 10 to negative 15 coulomb. Or you can write it as 1.95 femtocoulomb. Okay. Okay, so the most difficult part for this triple integral is that you need to know dv will be looking like this. This whole thing is the dv. dv in the spherical coordinate. So it turns out to be dr, d theta, d phi, and then multiplied by this r squared times sine of theta. And then finally, because all these three functions are just like multiplied, independently multiplied by each other. So this triple integral can be separated into 3 independent single variable integrals. So the calculation of each of them will be very easy. Okay, so for the second part, it asks you what is the field magnitude E at r equals 0. Okay, so this part is really easy. It will be E equals 0 at r equals 0, because if you just try to draw a very small Gaussian surface, and then it will enclose nothing, and then the E field will be 0 for that case. So at r equals 0. So this is the most easiest question. Okay, so for the part C, it asks you what is the E field at r equals to capital Alpha 3. Okay, so in that case, we need to calculate the Q enclosed. We need to partially recalculate this Q, because Q enclosed is only part of it. So in that way, we have a rho s over r, and then integrating r prime cube dr prime from only 0 to small r, from 0 to small r. Okay, we put a prime here because we need to keep this small r here. Okay, so this dummy variable and this one cannot be repeat. So we try to put a prime here so that to distinguish this one and this one. And then the remaining part will be the same because it's a whole speed. So it's sine theta d theta from 0 to pi, and then 0 to 2 pi d phi. Okay, so similarly, this one is 2 pi, this one is 2, this one will be r to the 4th power over 4, something like this. So the only different case is that this capital R and this small r to the 4th power cannot be cancelled. So it turns out to be rho s and then r to the 4th power over capital R. Yeah, something like this. We also have a pi here. We also have a pi here. Here we have a pi, and then here these 2, 2, and 4 cancel each other. Okay, so this is the Q enclosed, a little bit different from the question A. Okay, so here we try to apply the Gauss law for this Gaussian surface. Okay, so this Gaussian surface is like we have a sphere with a radius capital R. Here we only have a R. R equals 1/3. Okay, so this is the Gaussian surface. Okay, so we apply the Gauss law for this inner Gaussian surface. So we have epsilon naught integration of E dot dA equals Q enclosed. So in such a way, we have epsilon naught times E times 4 pi R square equals this one, putting it here. So it will be pi rho S R to the 4th power over capital R. So in this case, we can partly cancel this R square with this R to the 4th power down to R square. So in this case, we have E equals rho S. We can also cancel this pi with this pi. So here we have rho S times R square. Rho S times R square, and then we have 4 epsilon naught R, like this. Okay, this will be altogether correct when R is smaller than capital R. Okay, so this is the closed form solution. But here we would like to calculate when R is equal to capital R over 3. So when when R equal to capital R over 3, we have a rho S and then R over 3 square over 4 epsilon naught R. Which will be rho S times R over 36 epsilon naught. And then we can plug in all the numbers. Rho S is 35.4 times 10 to negative 12, and then times 0.056, and then over 36, and then epsilon naught is 8.85 times 10 to negative 12. So this turns out to be 6.22 times 10 to negative 3rd power Newton per Coulomb. Okay, so in such a way we can actually calculate the the E field at R equals to capital R over 3. So for question D, we need to calculate R equals to capital R. The lucky thing is that we already have the total charge. The total charge is actually the Q equals pi rho S over R cubed according to question A. So this is the total Q equals to epsilon naught E and then 4 pi R square. Okay, so we use the Gauss law for the whole sphere. So in such a way we can cancel the pi, and then finally we can have E equals rho S over 4 epsilon naught and then times capital R cubed over small r squared. Okay, so this is correct when R is larger than or equal to capital R. So here, if we would like to find R equals to capital R, we just substitute R equals capital R. So it will be rho S and then times R over 4 epsilon naught. And then we can plug in the number 35.4 times 10 to negative 12, and then times 0.056 over 4 times 8.85 times 10 to negative 12. So this one will be 5.60 times 10 to negative 2 Newton per Coulomb. Okay, and then we still have the graph the E versus R. So actually we know that the E have two expressions. So we have E equals rho S times R squared over 4 epsilon naught capital R. For R is more than R. Okay, so this one is derived in part C. This one is derived in part C. And then we have a rho S times R capital R cubed over 4 epsilon naught small r squared. Okay, for R is larger than or equal to R. So this one we obtain it at the part D. Okay, so we can plot this part out. So if we simply like, for this part we can observe that this is proportional to R squared. So which means that suppose this is capital R, this is R axis, this will be a square function. Okay, so this part E is proportional to R squared up to this point. This one, and then finally this one will be inversely proportional to R squared. So it turns out to be something like that. Okay, so E is inversely proportional to 1 over R, inversely proportional to R squared, or proportional to 1 over R squared. This point will be 5.6 times 10 to negative 2 Newton per Coulomb. Okay, for this point will be the maximum E field. Okay, so yeah, so of course this